Okay, hello everyone. We are going to be working on section 2.4, the arc length of a curve. And this is just the first half of 2.4, so I should have put 2.4 part 1 up there. On this section, we are going to be looking at arc length. So one thing that we can do with integrals, if we look at this equation right here, you can see we've got a curve f of x, some curve f of x. And we can break that curve up into little tiny segments. So we have segments A to B, and they've broken them up into individual little segments. So after we break them up, if we take just one of those segments, and let's look at that, that can be any one of these segments, then we can find the length between the 2 points. So the whole purpose to this, I'm sure you guys know, can see what's coming here, is to make delta x the limit of delta x, so the width goes to 0, right? So making that smaller and smaller and smaller and smaller until delta x is super close to 0. So what that's going to do is that's going to move these points closer and closer and closer together until they make almost an absolute perfect sketch of our function. So, but just to demonstrate how this works, we're going to take a really zoomed in picture of this. So the points, the 2 points, f of x sub I minus 1, and remember that's just how they're denoting that these two x values are different. So here's our first x value, here's our second x value, and the point, the y value, is going to be f of x and f of x. The difference between the x values is delta x, which we've talked about before, and the difference in the y values is delta y sub I. And the reason they're saying that is a y sub I is because every delta y is going to be different depending on which points you choose. Okay, so then using that picture there on the right, you can see that we can take the Pythagorean theorem and find the distance between our two f of x functions or values. So by the Pythagorean theorem, the length of the line segment is square root of delta x plus delta y squared. So delta x squared plus delta y squared. Okay, that's just the Pythagorean theorem. Then we can also write this as, I'm going to show you the intermediate step that they kind of left out there. There you go. So the step they kind of left out right here is here. We could simplify that a little bit if we multiplied the square root of delta x squared plus delta y sub I squared. Now let's go in and multiply that by the square root of delta x squared over delta, the square root of delta x squared. So we're just multiplying by 1, multiply the same thing, top and bottom. Now I'm going to leave this one out in front. So the square root of delta x squared, that one cancels to delta x. Then the other one I'm going to go ahead and multiply through our square root. So then we're going to have what, delta x squared over delta x squared, which is going to be 1, and we'll have to distribute that inside those that square root, plus delta y sub I squared over, oh dear, sorry. Okay. Jeez, my pen. It's not working again. Okay, I gotta pause a minute, get my pen to work. Okay, so I had to rewrite everything in there. So now the square root of delta x squared just becomes delta x out in front for the numerator. The denominator we're going to go ahead and distribute throughout the inside of our square root. So now we have the square root of 1 plus the square root of y sub I squared all over the delta y sub I squared over delta x squared. So now, because of, and it goes on to explain here, the mean value theorem, there is a point x sub I such that f prime of x is equal to the difference in the y's over the difference in the x's. So I want you guys to think back to our derivatives. Remember that our derivatives, or the slope of a line, is equal to the change in y over the change in x. So if you can see where we're going with that, we're going to be changing this into a derivative, all right? So we can say that because of that mean value theorem, there is at least one point in the derivative that is going to equal that. And then what we do from there is we take the sum of all of those points of the derivatives, and that's what becomes our integral. Then we take the limit as n approaches infinity, and once we take that limit as n approaches infinity of our delta y over our delta x, then we have the exact derivative. Which then brings us to our equation for arc length. So the equation for the arc length is the integral from a to b of the square root of 1 plus f prime of x squared dx. So if you look back up here when we took that delta x right here, remember that delta x we had left over out in front, that delta x becomes your dx. And then the limit of your summation then becomes your integral of a derivative. And then let's look at our first example. So our first example says find the arc length of y equals 4x plus 4 on the interval from 0 to 2. So let's go ahead and set up our integral. Our equation is going to be from 0 to 2, and then it says that we take, to find arc length, we take the integral, or the square root of 1 plus f prime of x. So we need to find y prime over here. So the derivative of 4x plus 4 is just 4, and then we'll plug that in here and square it, and then our dx out in front. Now we've got the integral from 0 to 2 of the square root of 17 dx. And when you take and integrate that, we have the square root of 17 17x evaluated from 0 to 2, which then gives us a final answer of 2 square root of 17. Okay, on this one, there are some examples, most of the examples actually that you do on here, you're going to need to use your calculator to determine the integral, or an integral calculator online. I'll hopefully be posting a video today also of how to use your calculator. I would like you to know how to do integrals on your calculator for these, and just for future references, that's a good thing to know. And other than that, you guys should be able to get started on your homework from there.